Hello, thank you for joining me. This is Psych 18, and we are now covering Chapter 12, Descriptive Statistics. So these are the objectives for today. We'll identify some activities that are included in descriptive statistics, talk about how research is analyzed, review how to make and use a frequency distribution, describe ways of presenting data, define characteristics of a frequency distribution, and we are going to review things like measures of central tendency, variability, some normal distribution problems, calculating percentile rank, z-score problems, Cohen's d, and correlations. A lot to cover. So with descriptive statistics, remember what we're doing here is we're trying to, in one numerical value, essentially summarize what's going on in a data set. So descriptive statistics includes things like counting, tallying, summarizing data, and correlations. So all of these activities comprise what we would call descriptive statistics. Just as a review, remember scales of measurement. That's so important because it has everything to do with the kind of analysis we're going to do on the data. So nominal scale variables, remember, are categorical. They're considered qualitative. These have absolutely no quantitative value. They are just different. For example, gender identification, ethnic group, your hand dominance, eye color, favorite color, all those things are just categories that are different from each other, but have no numerical value whatsoever. Ordinal scale variables are different, just like nominal scale variables, but now we have some sort of ranking. So it's a measure of magnitude. So with ordinal scale variables, we can actually distinguish something is greater or lesser than, but we don't know by how much. So still, ordinal scale variables are still considered qualitative in that sense, because we can't really do any calculations. All we can say is something is greater than or less than. We don't know the difference between those items. So for example, military rank, we know that a sergeant is higher than a private, but we don't know how much experience that requires for someone to get that to that may vary. There are certain duties they can perform, but how long it takes someone to move from one to another will vary. Award placements, first place, second place, third place. We don't know, for example, how much faster a first place sprinter is in the Olympics than a third place sprinter, right? We just know that the first place was the absolute fastest. And we might even say, in some ways, the grade levels. So those are things that are ordinal scale variables. Interval scale variables, now we're talking quantitative. So nominal and ordinal scale variables are qualitative. Interval and ratio scale variables are now quantitative. So interval scale variables are different, like nominal scales. There's a ranking, like ordinal scales. However, with interval scale variables, the differences between the first and second, is equal to the distance between the second and third. So it's very predictable. So calendar days are interval scale variables. IQ score, temperature, GPA, these are all interval scale variables. The 0 in an interval scale variable has no meaning, right? So that's the difference between interval scale and ratio scale variables. With ratio scale variables, it has what we call a true 0 value. 0 means the absence of the variable. So ratio scale variables are the ones we're most used to. For example, credit hours, weight, height, anything you measure, essentially response time, distance, those kind of things are all ratio scale variables. Any questions on these? So when we start to collect data and we think about research, there are really three main ways we analyze it. We're either comparing group percentages, we are correlating individual scores, or we're comparing group means. When we talk about research, for example, if we want to know if it's descriptive, we might just be talking about percentages. And I'll give you an example of that. If we want to know a systematic relationship between variables, then we're going to look at correlations. We might also look at how groups are doing in terms of performance. That's what we mean by comparing group means. How we do these analyses will depend on the scale of measurement we use and what kind of data has been collected. So when we compare group percentages, you might think it doesn't sound very meaningful, but actually it can reveal a lot. So this is what we do if we have nominal scale variables. It's really all we can do. So for example, in 2007, there was a MetLife study about homework. So the participants in the study were teachers, parents, and students. So you have three groups, right? Three categories, nominal scale variables. The question was, do you believe that homework is important? And the answers were yes or no. Again, nominal scale, right? So answered yes, 83% of teachers, 81% of parents, and 77% of students. So majority of people, the participants, did believe that homework was important. The second question was very revealing. They asked, do you believe homework helps students learn? Yes or no? So in terms of answered yes, only 55% of teachers, 59% of parents, and 29% of students said yes, they believe homework helps students learn. So this is a really simple study. It's a survey. We're talking here only about nominal scale variables, but the information is actually quite interesting. So even though the majority of participants who were teachers, parents, and students believed homework was important, there was a really big difference between how many thought it helped students learn. So if only 55% of teachers, for goodness sake, thinks homework helps students learn, why are we assigning homework, right? So even though this is a very simple study, it's actually quite revealing. And that's what we're really after in terms of psychology and research. We want to learn more about what's happening, and it's a way of quantifying that understanding. So we're not just talking about anecdotes, now we're getting real data. So for correlating individual scores, we can only do that. We do that when we have at least two variables to examine. We use this if there aren't any distinct groups. So in the previous example, we had three distinct groups. We had parents, teachers, and students. So now let's look at this one. Here's an example. Lowry, Dean, and Manders did a study on sleep and academic achievement, and they operationally defined academic achievement as GPA. So the research question was, is there a relationship between sleep and academic achievement? So what did they do? They asked people how much they slept, right? So now we're talking about ratio scale variables. So now what the study did is they correlated the individual scores on how many hours people reported they slept and their GPA. They wanted to see, is there a systematic relationship? And what did they see? They found, so the average amount of sleep did correlate with GPA. Out of 101 participants, there was a 0.2 correlation, which is actually quite weak. And p-value is 0.048. So people might be surprised that it's such a low correlation. But if you think about it, oftentimes the students who work really hard and spend many, many hours studying don't get a lot of sleep, right? So it's not that surprising that the correlation isn't extremely high. So now for comparing group means, so we looked at frequencies, and that's when we have nominal scale variables. We look at these correlations of individual scores when we're not really looking at distinct groups. We want to see what's happening in one group, but between two variables of that one group. Then we use comparison of group means if we have two or more groups. So for example, in that study with MetLife, with the parents, students, and teachers, if we had interval or ratio scale data, we could compare the group means, but we didn't. We only had nominal scale data, and so we were only looking at frequencies. So when you compare group means, what you're looking at the means of the dependent variable for each group. So here's an example. Wasink and Payne had a study on eating and environmental cues. So the research question was, do people eat more when there is no environmental cue or a reminder of how much they ate, or it's missing, right? Do they eat more? So the study, this would have been so fun to be part of. got to eat chicken wings. So they brought participants to a restaurant, and the groups were, they were male and female, men and women. And it's either they were going to an unbussed table, meaning they left all the wing bones on the table, or they ate at a bus table where the servers continually took away the bones. So unbussed table means there's a reminder of how much you're eating, right? A bus table means it's gone. So if you look at this, men ate 163.3 grams of chicken wings when it was unbussed, meaning they saw the bones. In a bus table, they ate 264.8 grams. So they just kept eating when they weren't seeing, how many bones there were. Women ate an average of 207.3 grams of chicken wings on the unbussed table, and also increased with the bus table, but not as much as the men, right? So men, when they didn't see the cues, ate a lot more than the women did. So it's kind of interesting. So here's an example of where we're comparing group means. So you don't need really complicated data to get an understanding of people's psychology. And that's what's really important to take away. So when you have data, now we're talking about interval ratio scale data, you want to present it to people in a way that's easy for them to understand. So there are different ways we can do that. And we call it a distribution. So distribution is the way that scores on a variable are scattered across levels of that variable. I'll kind of show you what that looks like. So a frequency distribution is simply a way that we map the information. It's a way of organizing the data that we have. And we can do that with pie charts, bar graphs, frequency polygons, or histograms. So let's talk about how you would even make a frequency data. So let's say you have this data set. You just have these numbers, 11, 8, 9, 12, 9, 10, 12, 13. It could be a score. These could be scores on some kind of a quiz or something, right? So when you have it, what you would do is, first of all, you order the data. Because right now, it's true, when you collect scores, it's just random, right? You don't know how people are scoring on it. So the first thing you do is you want to order the data. So here's the data that's ordered, 6, 8, 9, 9, 10, 10. Once you order the data, now you get a sense, right? First of all, of the range. The range is simply the highest score and the lowest score in your data set. Once you know the range, you can make the table. So this is what a frequency table looks like. So you know, once you've ordered it, that the lowest score is 6 and the highest score is 17. So you put every number between 6 and 17 in your table. And then on the right side, simply indicate the frequency. Now, if you look at the original data, we don't have 15, we don't have 16, we don't have 14. But in your frequency table, you have to account for that. So every single value between the lowest score and the highest score needs to be listed in your frequency table. And then you list how often they show up. Really easy. That's a frequency table. Another way we might display data is through a pie chart. So we often use pie charts for nominal scale variables, right? It's an easy way to show frequency. And you can either do it as the raw number, or you can do it as a percentage. So for example, in a study that examined how often children were read to at home, if you look at the ends, the raw data, it's 48 kids were read to and 12 were not read to. So one way we can simply represent this is in a pie chart that shows 80% of students that were participated, parents read to them, and 20% did not. When you're looking at data, it's a good, proportions give you a good sense, but it's also important to get the raw numbers. So you know just how big the sample size was, and you can critically evaluate how representative is that sample size. Any questions so far? Right, bar graph is another way that we represent data. And a bar graph, we use that again for nominal data. It's important to notice, right? It's a distinct bar for each piece of information. The bars do not touch in a bar graph. So here we simply have two different colors that represent whether children were read to or not read to. And then on the y-axis, which is the vertical axis over here, we simply indicate the frequency. An easy way to represent data. A frequency polygon, whoa, that didn't look right. That looks weird, okay. This is what a frequency polygon looks like. So here in this study, what we looked at was how much children like their parents, mothers or fathers, right? So fathers were the dark blue line and mothers were the orange line. And so 1, 2, 3, 4, or 5, right, is how many children reported that they like their moms more than their dads. And so you get kind of a sense of how it's flowing. It's kind of funny study. So with the frequency polygon, you use interval or ratio scale data. A count would be ratio scale data. And the lines represent the distribution of scores, and we just plot the frequency of each score. Histogram, we're going to look at quite a bit. So with a histogram, we're looking at quantitative data. In a histogram, as compared to the bar graph, the values are continuous, and so the bars in a histogram are actually touching. And it's really important to interpret the graph correctly. In a histogram, what's advantageous is you can easily see where outliers are. It's going to be really obvious in it. And usually the normal distribution, which we'll talk about, is depicted as a histogram. When we look at histograms, we look at the shape of the graph. So a peak is the high point in the distribution. Tails are the ends of the distribution, right, at the extreme ends. Unimodal is what we call a distribution with only one mode, meaning one top score. And bimodal means it has two distinct peaks. And the other part we look at is symmetry. How symmetrical is this graph? So if it's symmetrical, then the distribution on the left and right sides are almost mirror images. They don't have to be exactly mirror images, but very close to being mirror images. So important terms to know. So here is the classic normal distribution, also known as the bell curve. So you can see that the graphs, the bars, this is a histogram, right? Each bar is 0, 2, 4, 6, 8, 10, 12 over here. Those are the values on the x-axis, and the frequency is on the y-axis. If you look at the bars themselves, it is not a perfect mirror. But if you kind of draw a line that follows the shape of the tops of the bar, that's what we mean by saying it looks symmetrical. We'll talk about characteristics of normal distribution in a bit. So this is an example of a histogram with a bimodal distribution. So the peaks don't have to be equal, but they have to be noticeably higher than the other values in order for it to be bimodal. So when we talk about distribution shape, right, if it's symmetrical, as I mentioned, it's almost like mirror images of each other. If it looks like it's pulling to one side or the other, we say that that shape is skewed. So negatively skewed means that it has a long negative tail, meaning there is an extremely low value towards the negative, and that's why we call it negatively skewed. If it is positively skewed, then it has a really long positive tail, means that there's an outlier. Somebody scored really, really high on the exam. That's what would pull it to a positive skew. So the outlier would be the value that I just said that will cause the distribution to have a really long tail. So when you collect data, sometimes you're going to have, for example, maybe one student who scored really, really low on a cognitive assessment, and that's going to skew your distribution to the left, to make it negatively skewed. If you don't have a really large sample size, these negative outliers are going to really impact the way your data looks. So you really consider, you want to have as large a sample size as possible to minimize the effect of these outlier values. The other way we deal with it is we simply do not count the outlier value. And then when we report the data, we indicate at what point we determine the outlier. Usually it's going to be more than 3 standard deviations from the mean. Right, so central tendency is what we call the value that helps us determine how participants scored overall. There are 3 measures of central tendency. We have the mean, which is the sum of all the scores divided by the number of scores. We can only use this for interval or ratio scale variables. If you have an ordinal scale variable, you will have to use median or mode, right? So median is the middle score. If you have an even number of scores, you take the average of the middle 2, and that would be your median. So for median, we can use that for ordinal, interval, or ratio scale variables. And finally, we have mode. Mode is simply the most frequent score. We can use that for any scale of variable, nominal, ordinal, interval, or ratio. So if you have nominal scale values, your data, you're very limited to what kind of central tendency you can use, right? So the more, when you have quantitative values, you have more choices in how it's going to be used. You also want to be careful because if you have really extreme scores, the mean is easily influenced by outlier scores. So you might not want to use mean. Maybe you want to use median instead. So that's why, for example, housing values, we don't use the mean value of or mean cost of a house. We use the median. Why? Because we live in a place where they have $5 million homes. If we took the mean, it would really influence the average value of a house. So when you hear the average value of a house, they're really talking about the median, not talking about the mean, because we want to avoid the extreme scores. So calculating central tendency, just a refresher from statistics, right? Mean, you add up all the scores, you divide it by the number of scores. For median, you order the scores from lowest to highest. Then for even number of scores, you calculate the mean of the middle 2. And then for odd number scores, you just use the actual literal middle score. And mode is the most frequent score among all of them. So if I were to give you a data set, I might say, find the mean, median, and mode for the following set. So I would provide you the frequency distribution and the data. So remember, for mean, you would add the data, right? So we could look at the frequency table. 17, we have one value of 17. We have 2 values of 13, 3 values of 12, 2 of 11, 2 of 10, 2 of 9, 8, and 6. And you have the total of 141. And then you divide by how many. So you have 15 scores here. The mean is 9.4. For median, you would order the data, right? Then you find the middle value. So you have 15 divided by 2, 7.5. So you simply count up where that is in your ordered data set. And the middle value is 11. Really easy for median. And then mode is simply look at the frequency table, right? What are the highest values? 12 and 13. So this would be a bimodal distribution. Any questions about central tendency? Nope. Easy peasy, right? Okay, so in addition to central tendency, we're also interested for descriptive statistics to look at variability. So variability is simply how much spread is there in the distribution of scores, right? How far apart do they fall? When we talk about variability, we might talk about range, which is simply the difference between the highest and lowest scores. And we can look at deviation. So deviation is how far from normal, normal meaning the mean of the sample. So when we say standard deviation, what we're actually looking at is the average deviation of scores from the mean. That's literally what it is. So it's if we took the value of each score and subtracted the mean from it and took the average of that. That is how you calculate standard deviation. So standard deviation tells us how far away the scores are from the mean. This is an example of a normal distribution right here. The further the spread is, the larger the standard deviation. If you have a situation where your standard deviation is 0, that means there's no variation. It means all the values in the set are exactly the same. I can't think of really very many situations where you would get that, but that's what you should be aware of. So if you look at this distribution, what you see here is that most of the scores fall in the middle, right? That's what the normal distribution shows. There are very few with high scores and very few with low scores. That's why those are the extreme parts. So the majority fall in the middle. This is an important characteristic of the normal distribution. If we see a curve that looks like this in the top here, that is what we call a small spread. The standard deviation is very close to the mean. It's small. That means the scores are really close to the mean. There wasn't much variation. If I saw that in terms of the midterm exam, for example, that means most students scored close to the average. No really high scores, no really low scores. On the other hand, if there's a large spread, right, it means that there was a lot of variation in the scores. So for the normal distribution, it has specific characteristics that we think is very important, helps us predict things. If a curve is normally distributed, you can apply what we call the 68, 95, 99 rule or 99.7 rule. Here's how it goes. Mu is that funny looking U in the middle. That is the mean score. What this rule tells us is that 68% of the scores fall within one standard deviation of the mean. 68, that's more than half of the scores would be within one standard deviation. 95 means that within 2 standard deviations of the mean, you have 95% of the scores. And then the 99.7% rule says that within 3 standard deviations of the mean, 99.7% of the scores will fall in that. And that's why when we talk about outliers, we often define an outlier as a score that is more than 3 standard deviations from the mean. So it's important to have a good understanding of the normal distribution because we have some calculations to do. So just for an example, IQ scores fall with, it has a normally distributed scores. So the mean IQ of the population is actually 100, and the standard deviation is 15. So when you have a normal distribution problem, this is what I recommend. Mark off where the mean is. So you draw a diagram similar to this with a normal bell curve. Mark off where the mean is. So if you look 0, there's the 100. That indicates where the mean is. Then calculate standard deviations, at least 3 standard deviations out. So 100 minus 85, minus 15 is 85. So that's 1 standard deviation below the mean. Subtract another 15, you have 70. That's 2 standard deviations below the mean. Subtract again, you have 55. And that's 3 standard deviations below the mean. And do the same for above the mean. So now you have the range 55 and 145. So you know now that all these scores, right, within 3 standard deviations of the mean are going to fall between a score of 55, an IQ of 55, and an IQ of 145. So 99.7% of the population have an IQ with a range that goes between 55 and 145. So this helps ask a lot of questions. So we could say, between what scores do the middle 95% of participants fall? Well, according to the 65, 95, 98, 99.7 rule, right, we're going to expect it to fall within 2 standard deviations below and 2 standard deviations above. So middle 95% of the population will have an IQ between 70 and 130. Then you might say, what percentage of participants' scores fall between 85 and 115? Well, that's within 1 standard deviation of the mean. So because of that rule that we know it's 68% of the population falls between that. And so I can ask you questions that vary And the idea there is to test your understanding of the normal distribution and how it works in terms of standard deviations and population percentage. And we'll have some sample problems with that too. So homework 5 is calculations. It's mostly calculations and reviewing of this normal distribution rule. Oops, there we go. Percentile rank is another calculation that hopefully you remember from your Math 63 class. So with percentile rank, we're just talking about the percentage of scores in the distribution that are lower than a particular score. So how do you calculate it? You count the number of scores in the distribution that are below your score of interest, and then convert the number to a percentage of the total scores. So for example, Groot earned a score of 98% on his midterm exam, which was the second highest score. He was in a class with 45 students. What was his percentile rank? So what you would do here is you would figure out, okay, whoops, sorry. There we go. Out of 45 students, right, he got the second highest. So 43 scored lower than he did, right? 43, and then what you do next is you figure that out as a percentage. 43 out of 45, sorry, it's gonna come out weird. There we go. 43 out of 45 is 0.955, convert that to a percent, so it's 95.5%, you can round that. Groot is in the 96th percentile of exam scores. So that's how you would calculate percentile rank. Does that make sense? Yeah, okay. Okay, another calculations that we are going to go over are z-scores. So there's the formula for a z-score. Z-score is simply the difference between a score that you're interested in and the mean of the distribution. So X represents the score you're interested in, and M is the mean of the distribution. And then once you have that, you divide it by the standard deviation of the distribution. It's a really useful score because it helps us to compare scores on different scales. So for example, if midterm 1 was out of 60 and midterm 2 is out of 75, it helps you to calculate, how did they do relative to the class, right? Because of the mean, which score did they get higher? And that's really a lot of times the example that I give you. So it's important because it is expressed in standard deviations, and that's why the scale doesn't matter. What you're looking at here is standard deviation. It helps you to identify outliers as well, and helps you to compare scores using different scales. And I'll go over how to do z-score problems after. Cohen's d is another really important value that you will see oftentimes in the peer-reviewed journals. Cohen's d is also known as power, the effect size. So this is it describes how strong the statistical relationship is. And this is what we use to analyze differences actually between groups, right? This is what we would know. It's a difference between the means of group 1 and the means of group 2, again, divided by standard deviation units. You will see effect sizes very often in a meta-analysis. We use this because in a meta-analysis, we're comparing results from different studies. So they're using different scales most of the time. So with a meta-analysis, it gives you a sense of, okay, even, maybe a sense of self-esteem, the power of the effect of self-esteem on cognitive performance or something that you might see that in many different studies. They are often using different scales of measurement. And so you use Cohen's d to get a sense to equalize, maybe basically standardize how cognitive, how self-esteem is affecting cognitive performance. So when you're looking in a peer-reviewed journal, understand that if they say there is a strong or large effect size, the Cohen's d is going to be 0.8 or higher. Correlationally, they might some plus or minus 0.5 in terms of Pearson's correlation. If it's a medium effect size, right, Cohen's d would be about 0.5. So between 0.5 and 0.79 is a medium effect size. Pearson's R, correlationally, might be about 0.3. And then a weak effect size is 0.2 in terms of Cohen's d, and Pearson's R is 0.10. The weaker the Cohen's d, the more participants you need to see the effect, right? If you have a really strong effect, you don't need that many participants. You're going to see it happen. But if you're looking at some kind of psychological construct that has a weak effect, then understand it will take many, many participants to actually see the effect occur in your study. So correlations, we've discussed that one quite a bit, right? So positive correlation, values go in the same direction. As X increases, so does Y, or as X decreases, so does Y. And then, negative correlation is they move in opposite directions. So correlations are very, very common in studies. And here is kind of scatter plot, how it would look. You are never going to see a perfect positive correlation or perfect negative correlation. But what you'll more likely see is modest positive correlation. So you would get this, you have scatter plot when you have your data, you collect your data, and you're starting to plot where people fall, between their x-axis is the independent variable, y-axis is the dependent variable. If you're lucky, you'll see something fairly clean like this modest positive correlation. If you're unlucky, you're going to have no correlation and your hypothesis will not be supported. So here are like kind of the benchmark values in terms of correlations. If it's below 0.16, positive or negative, right? We say that's very low correlation. 0.16 to 0.29 is weak to low, 0.3 to 0.49 moderate to low, 0.5 to 0.69 moderate, 0.7, 0.89 strong, and 0.9 to 1.0 very strong. So just benchmark values. Oh, ready to do some problem review now. All right, so let's take a look. Recap that here is that normal distribution. Remember 68, 95, 99 rule. 68% of the values will fall within one standard deviation. That means above and below. 95% of the values will fall between 2 standard deviations, and 99% will fall within 3 standard deviations. So here's an example problem I could give you. The weights of stray dogs at a pound have a mean of 70 with a standard deviation of 2.5 pounds. Assuming the weights follow a normal shape distribution, what weight is 2 standard deviations below the mean? So, like I said, I would say draw that little diagram. So right in the middle should be 70, right? That's the mean. Mark off 3 above and 3 below for the standard deviations, and then you calculate it, right? So 70, take away 2.5, you're going to calculate that. You're going to calculate 1, 2, and 3 standard deviations below the mean, and you're going to calculate 1, 2, and 3 standard deviations above the mean. First thing you should do when you get this problem. So then if I say what weight is 2 standard deviations below the mean, it's really easy for you to answer, right? So 70, take away 2 times 2.5, which is 5. So the weight of 65 pounds is 2 standard deviations below the mean. Very easy to answer, especially if you've already drawn that curve, right? So this is what I would recommend you do for any standard normal distribution problem. Okay. Here's another question I could ask. Same thing. So I could, and this is what I do, is I have, a problem and I'll just do variations of it. Same thing, 70, mean of 70 pounds, standard deviation of 2.5. The middle 68% of dogs weigh how much? So if you drew that, you'll know, right? This is testing your understanding. 68%, remember, that's within 1 standard deviation of the mean. So Middle 68% are within one standard deviation of the mean. So you would look one below is 68.5 and one above 72.5. And then you could answer that the middle 68% of dogs weigh between 68.5 and 72.5 pounds. Easy enough, right? Okay. And here's another example. Oh, I just put the whole answer there. Where it could be a mix of things. So here is what percentage of dogs have weights between 62.5 and 77.5 pounds. So you look at your diagram, 62.5 is 3 standard deviations below the mean. 77.5, right? 77.5 is 3 standard deviations from the mean. So you know that 99 or 99.7% of dogs have the weights between 62.5 and 77.5. So those are different types of variations that I would do with normal distribution. Any questions? Okay. Z-scores. So remember, we're talking here now about a score of interest, the difference between the mean value of a group and an individual score, and we divide that by standard deviation. So here's an example Z-score problem. Bruce took an exam with 35 questions on it. His score was 20. So 20 out of 35, right? The class or mean of the midterm is 26.16 with a standard deviation of 4.52. The final exam has 100 questions and Bruce's score was 65. The class mean of the final is 80 with a standard deviation of 14. A big standard deviation. Was Bruce's score on the final exam relative to his classmates better than his relative score on the midterm? So this is an example of where you could use Z-scores, right? So the key here is that it's relative to his classmates. If we're just talking about Bruce's score, it's easy enough. We would just look at 20 out of 35 and 65 out of 100, and which one's better. You need the Z-score formula because we want to know how he did in relation to his classmates. So the solution for this, here we go. So the Z for the midterm, right? His score was 20 minus 26.16. That's the mean of the class. And you divide it by the standard deviation of 4.52. So negative 6.16 divided by 4.52 equals negative 1.36. What does that mean? It means Bruce's score was 1.36 standard deviations lower than the class. That's the interpretation of that. So he didn't do so well, right? But now let's see, how did he do in terms of the final exam? Well, you calculate the Z-score for the final. His score was 65. The class mean was 80, and you divide it by the standard deviation of 14. So negative 15 divided 14 equals negative 1.07. So Bruce's score was 1.07 standard deviations lower than the class for the final exam. So which one did he do better in? Was it the midterm or the final? Well, being 1.36 standard deviations lower than the class is worse than being 1.07 standard deviations, right? You're further away from the mean. So the answer here would be, relative to the class, Bruce's performance on the final was better than on the midterm. Now, if it were the opposite, if Bruce's score was above the mean, right, then his performance would be better on the midterm than the final. So you have to read the context of it. If you're talking about doing worse, you want to be closer to the mean. If you're talking about doing better, then you want to be further away from the mean, right? So make sure you pay attention to the context. I will ask you for interpreting the values, because anyone can plug in numbers in a formula. I want to know if you can actually understand what the formula, what the answers are telling you. All right, so another example is Z-scores. Okay, Diana took an exam with 40 questions on it. The class mean of the midterm was 30.5, standard deviation of 4. Her score was 33. The final exam has 100 questions and Diana's score was 88. The class mean was 82, standard deviation of 12. Was Diana's score in the final exam relative to her classmates better than her relative score in the midterm? So go ahead and try it. And then you could tell me. Do you want to do it? Or should I just go through it? Okay. I won't put that pressure on you.
I will take a picture because I want to think about it. This score, it was one of the challenging for me.
Oh, okay.
The previous one, it's the easiest. Here, a little bit I have to think.
Okay, well, we'll do some practice in class too. But so same idea, you're going to calculate the z-score for both, right? You're going to calculate the z-score for the midterm and you'll calculate the z-score for the final. So whoops, I kind of messed that up. Okay, z-score for the midterm. I think there it is. There's all the information. Okay. Her score was 33. The class average was 30.5. You divide by the standard deviation. And so it's 2.5 divided by 4. She was 0.625 standard deviations above her the class. For the final, she had 88. The class average was 82, divided by the standard deviation of 12, and it was 0.5. So she was 0.5 higher than the class for the final. So Diana's performance relative to the class was better on the midterm than on the final, right? Because she's 0.625 standard deviations higher than the class average for the midterm, whereas for the final, it was 0.5. Okay, so that is just kind of the review for descriptive statistics. Let me stop this.